family name on the periodic table. What is that? Noble gases. All right. The last family, group 18, is called noble gases. Now remember, groups run top to bottom. How many groups are there total? Total is 18 groups. All right. Groups run top to bottom. How do periods run? Periods run left to right. You end a sentence with a period. How do you write a sentence? Left to right. Does that make sense? There are 7 periods and 18 groups on the periodic table. Now, this group 1 is called alkali metals. Alright? Hydrogen is not an alkali metal. The remaining elements are called alkali metals. The next group is group 2, so it contains 2 words, alkali earth metals. Alright? Then this D block is called the transition metals. They're all in between or transition metals. Alright? The last 17, group 17, is known as halogens. Alright? We are not going to go to the other groups. We are just going to call it based on the first element. Oh, it's the oxygen. Oxygen family actually has the name chalcogens. Chalcogens. We don't want to know that. Alright? C-H-A-L. Chalcogens. Alright? We should definitely know halogens, noble gases, alkali and alkali earth metals. Alright? Now, if you actually look at the periodic table, you realize that this is how the periodic table should be arranged. There should be the S block. Is that right? There should be the S block. And then, after the S block, there is a small 2 elements in the D block, which is the lanthanum and the actinum, which is 57 and 88, 89. Is that right? And then comes what? The F block. Then comes what? The D block. And then comes the P block. That's how the periodic table should look if you're writing electron configurations. Is that right? But what did they do with this F block? They cut it off and brought it to the bottom. Is that right? Are we aware of that? That 57 and 58 and then in 58 and 90 are actually F block elements which end in 71 and 103, and then the D block elements follow. Is that how you write your electron configurations also? Are we aware of that? Okay. So since this block has actually been chipped off and put here, this is known as the inner transition elements. Inner transition elements. Or sometimes they will also call this line the lanthanides because it follows lanthanum. And then they will call this row the actinides because it follows the element actinum on the periodic table. Does that make sense? Okay? So now let's go on to our continuation notes. And we did say which were the elements that do not follow the rule. The D4 and the D9. Right? They are exceptions to writing the electron configuration. Is that right? So right now, let's go ahead. Did I do copper in class last time? Should we do molybdenum? Did we do molybdenum? We did molybdenum also. It should end with a D10, right? You pull one electron from the s orbital. All right. Now, you have drawn Bohr model. For instance, let me draw the Bohr model of oxygen. Oxygen has a total of 8 electrons, right? So oxygen is in energy level 2, which means you draw two circles and you put two electrons in the first energy level, 2, 3, 4, 5, 6, 7, 8. Is that how you draw the Bohr model for oxygen? How many electrons are present in the outermost energy level? How many electrons are present in the outermost energy level? 6. All right. These electrons that are present on the outermost energy level are called valence electrons. What are they called? Valence electrons. So let's pull in the definition. Valence electrons are the electrons on the outermost or highest energy level, or the highest energy level. What do you think is the maximum number of electrons that can go into the outermost energy level? Yeah. The Bohr model one? Which, oh, you want extra copies of this? Do you, anybody who doesn't have the note sheet would like an extra copy of it? Because you don't have, so 4 here. Pass one to Alex also. Here's here. Here. Anybody else? Do you need one more? Here. Here. I think we need one more. Is there enough extras? Everybody got one? Everybody has this note sheet in front of them? Husky, did you? I wasn't very clear about the question you were asking. Last class we passed it out. Do you have a copy of it? Right now I'm passing out extra copies. Here, use this to fill in the notes. You need one as well, Brianna? Anybody else who doesn't have this note sheet? I'll give you extra copies. Mario, do you have this with you?
Yeah.
Are you taking notes?
Yes.
Everybody should be writing notes, filling in notes. It's okay if you have a copy at home. Okay, moving on. So, okay, we didn't finish this line. The maximum number of valence electrons, what do you think the maximum can be? 8. It can be more than 8. Well, you may wonder what about the D and the F, which is 10 and 14. Is that right? You will realize when you write electron configurations that invariably the D gets tucked inside the S and the P, and it's never the outermost energy level. Okay? So it will never be the highest energy level. Noble gases tend to be stable and unreactive because they have 8 valence electrons, which is an exception to this rule. Helium, all right? Helium only has 2. Helium has 2. All right? Because they have, instead of 8, you can say they have a stable electron configuration. All right? They have a stable electron configuration. Now, we talked about ions in Unit 3. How are ions formed? Adding or removing electrons. Remember, you can't reach into the atom, deep inside the atom, or touch its protons or neutrons. All right? So, ions are formed by adding or removing electrons in order to mimic noble gases. Okay? So here's my oxygen. My oxygen wants to have 8 in its outermost valence electron, and so it gains 2 electrons and becomes 8. But it's still the oxygen element, and just because if it adds 8, what is its total number of electrons now? The total is now 10. Is it a noble gas? It's still an atom of oxygen. Why? The protons is what decides what the element is. Is that right? So atoms form by adding or removing electrons in order to mimic noble gases. They do not become noble gases because the number of protons has not changed. And this is known as we will go with the word isoelectronic atoms and atom and slash ion. Meaning, iso means, the word iso means what? Same number of electrons. Alright? If you compare neon and oxygen, they have the same number of electrons. They, in some ways, mimic each other, but they are not the same because the number of protons is different. Do we understand this? Okay. So now they are asking us to compare the electron configuration of lithium, sodium, and potassium. All right? You have to remember that in a periodic table, lithium, sodium, potassium follow one below the other. Is that right? On a periodic table, they all fall in group 1. So, if you write out their electron configuration, what will lithium's electron configuration end in? 2s, 1. What will sodium's electron configuration end in? 3s, 1. What will potassium's end in? 4s, 1. Because their electron configuration ends in s1, how many valence electrons will these elements have in group 1? 1, all right? So they have 1 electron in their outermost shell and they have 1 valence electron. Now, if you were to draw the Lewis dot structure for, say, sodium, sodium is in energy level 3, so it has 2 in the first, 8 in the second, and 1 in the third. Now, sodium wants to mimic a noble gas, meaning it wants to have 8 in its outermost shell. Right now, how many does it have? This is sodium, not oxygen. I moved on to the element sodium. So sodium has how many in its outermost shell? 1. What do you think is easy for sodium to do? Is it easier for it to lose 1 or gain 7? Lose 1. So what will happen is, sodium invariably will lose 1, and now there is the inner shell with how many electrons? 8. And now it's like a noble gas with 8 valence electrons. Does that make sense? So, group 1 elements will lose their 1 electron. If they lose 1 electron, what does their charge become? Positive 1. Alright? So, there is a lot of repetition of this through... Do you have that again and again? No, you don't. Alright? So let's move on and do some more examples. Alright? It's not given in your page, but let me do some more examples. Say you're going to group 2. Alright? If you are in group 2, they all end with what? S2 electron configuration. Is that right? So how many valence electrons will they have? 2. Alright? They will lose 2 electrons. So what is the charge that group 2 elements will have? Plus 2. So let's write down. Group 1 has 1 valence electron. What is the charge? Plus 1. Group 2 will have how many valence electrons? 2. And what is their charge if they drop the 2? Plus 2. Now, when you go to group 13, or if you go to boron, alright, if you write boron's electron configuration, it is 2s1, 2p, 2s2, 2p1. Is that right? That's the outermost electron configuration. You have to ignore the 1s2 because it's the lower energy level. That is boron's outermost electron configuration. How many valence electrons does boron have? 3. If you look at aluminum, aluminum's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. If you look at the highest electron configuration, how many valence electron does aluminum have? 3. So, all group 13 elements will have 3 valence electrons. Is it easier for them to lose 3 or gain 5 to get to 8? Lose 3. So they'll, oh wait, this is plus 2, right? Sorry, this is plus 3. Did you write that as plus 3? Sorry. It's plus 2. It'll lose 2 to become plus 2. Does that make sense? I don't know why I wrote 3 there. Right? You sure I make all such mistakes all the time. Alright, now, if you come to 4, 4 is halfway of 8. So if you look at carbon's electron configuration, if you look at carbon, it's 1s2, 2s2, 2p2. Ignore the inner shell. Carbon has 4 valence electrons. Now 4 is halfway of 8. It can either lose or gain. So the carbon group, all of them, if you write the electron configuration, will have 4. They will lose or gain. If you write nitrogen's electron configuration, let me erase this and go to nitrogen, alright? Nitrogen's electron configuration is 1s2, 2s2, 2p3. What is the number of valence electrons? 5. Is it easier to gain 3 or lose 5? Gain 3. So, though they have 5 valence electron, it will gain 3, which means the charge becomes -3. So the pattern follows, it's 6 valence electrons, they will gain 2, 7 valence electrons, they'll gain 1. Noble gases do not gain or lose, they do not make ions. Does that make sense? Do you understand this pattern? Okay, now let's move over to the next page. So you have argon. Argon has 18 electrons. So if you draw the orbital diagram for argon, all right, it'll look like this. All right, 3p6 is completely filled. Let's look at the periodic table now. Let's look at the periodic table and let's locate argon on the periodic table. All right? All of you look argon on the periodic table. Which is the element that can gain an electron and have the same number of electrons as argon? Chlorine. Do you see that? Which is the element that can gain 2 electrons and be isoelectronic with argon? Sulfur. Which is the element that can lose an electron and be isoelectronic with argon? Which is the element that is isoelectronic by losing 2 electrons? Calcium. They all have 18 electrons. They are different elements because of the number of protons, but they are isoelectronic because they have the same number of electrons. All right? So Cl minus would be the element. S minus 2 will be the one. K plus will be the one with a positive 1 charge. Ca plus 2 will be the element that will lose 2 electrons and still have 18 electrons. All these are isoelectronic. It's a single word actually. If you see the word isoelectronic of each other, you should not get puzzled. What is the word? What does it mean? All right? Now, not only do you have to know the electron configuration of regular atoms, but you should also know to write the electron configuration of ions. So phosphorus, if it gains 3, what is its electron configuration? How many total electrons does it have? Phosphorus -3 is 18. So its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. Because it's phosphorus, it doesn't end in 3p3. It actually ends in 3p6 because it has gained 3 electrons. Do we understand this? Now, this one is a very, very tricky example. Iron Fe plus 2. Okay? I'm going to do this stepwise. I'm going to skip the Fe3 first, and I'm just going to write iron first, then we will go to Fe plus 2. Alright? We'll do it stepwise. So if you look at iron's electron configuration, it is, let me write the noble gas configuration for iron. It will be argon followed by 4s2, 3d, what is iron's location? 1, 2, 3, 4, 5, 6. Alright? Now, the D level, you call it the next higher energy level in which the electron is being added. Is that right? The higher energy level is not actually the outermost energy level. What does that mean? If you look at the d orbital, if you look at the central nucleus, all right, it is, the d orbital is kind of like a flower petal. Is that right? Yes or no? This is the region where the electron is a wave and it's spinning around. That's the probable location. Is that right? If you look at 4s, 4s is a circular orbital. Is that right? Is that right? And it kind of spreads out. When you try to remove an electron from these electron clouds, all right, where do you think the electron is more easily available? In the 4s or the 3d? Where do you think you can pull out an electron more quickly and easily? From the 4s, not from the 3d. Even though the 3d is a higher energy level. Does that make sense? This is more readily available to be pulled out. So when you make the ion Fe plus 2, which electron is lost? The 2 electrons that are lost are first lost from the 4s and not from the 3d. So they ask you to write out the electron configuration for Fe plus 2. How will you write the electron configuration? It is Ar 3d 6. And you will not pull out the 2 electrons from the d orbital. Is that clear? Do you understand this? Now, I'm going on to Fe plus 3. The next element is Fe plus 3. Now what choice do I have? Do I now have to remove from the d orbital? You know what? Iron will remove it from the d orbital and it becomes 3d5. Is that right? Iron actually exists in these two. Why are the d blocks put in the middle? It's because they're crazy. In their compounds, they'll show multiple charges. If you knock out, you have extensive iron 2 compounds, you have extensive iron 3 compounds, and they look very different from each other. And why there are iron 3 compounds? D5 is a half-filled shell. It's stable for the element. Does that make sense? But will it also make Fe2 plus compounds? Yes, it will also make Fe2 plus compounds. So when you go to the D block, they have all these different charges. So we learned the Bohr model where we draw circles and denote all the electrons in the different energy levels. Is that right? As the name says, in a Lewis dot diagram, what do you draw? Dots. And what do you denote with the dots? Only the valence electrons. All right? So, let's look at sodium. Sodium is in group 1. Remember we drew the periodic table and we wrote out the valence electrons? All group 1 elements will have how many valence electrons? 1. Group 2 will have how many? 2. Group 13 is 3, 4, 5, 6, 7, 8. Remember that? So sodium falls in group 1. What is the Lewis dot structure for sodium? Just a dot. Magnesium falls in group 2. What is the Lewis dot structure for magnesium? 1, 2. You choose the 12 o'clock, 3 o'clock, 6 o'clock and 9 o'clock positions. Aluminum is in group 13. How many valence electrons? 3. Sulfur is in group 16, so it has 6 valence electrons. 1, 2, 3, 4, 5, 6. You double up, all right? You double up. These two should be shown single, all right? Chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And argon has the complete shell. 1, 2, 3, 4, 5, 6, 7, 8. Are we good with drawing Lewis dot structure? They can ask you any element. Oh, it's barium all the way down. Does it bother me that barium is all the way down? No, it's just 2 valence electrons still. Does it bother me that polonium is all the way down? No, it's still 6 valence electrons. Do you understand? Okay? Now, for the D block, all right? For the D block, we generally say the S fills before the D. But the S is the one that's readily available. Is that right? The outermost that gets pulled out when you make ions. In general, we say all D block elements will have how many valence electrons? 2, because those are the 2 that get pulled out first to make the ion. Does that make sense? So any D block element can get denoted with 2 valence electrons, but hey, it can reach in and sometimes you can take the 3rd electron out. Just a Lewis dot structure, just put 2 if they ask you a D block. Does that make sense? Do you understand? All right. N notation. All right. N notation again has to do with the writing the electron configurations using the periodic table. All of these elements in group 1 end with what? It's 1s1, 2s1, 3s1, 4s1, 5s1. So the general, instead of writing 1, 2, 3, 4, 5, what do you write as the N notation for group 1? NS1. Does that make sense? Do you understand it? For group 2, how is it going to end? S2, S2, 1s2, 2s2, 3s2, 4s2, 5s2, and so on. So what will be the general electron configuration for group 2? NS2. If you go down to group 13, it will be what? 2s2, 2p1, 3s2, 3p1, 4s2, 4p1. So what is the general electron configuration? NS2, NP1. What about group 14? What do you think it is? NS2, NP2. Correct. And then, if you go all the way down to noble gases, if you go to group 18, what do you think it will be? What do you think it will be for group 18? NS2, NP6. Let's think about the D block. If I go to group, let's think about the D block, all right? In the D block, now it is, for after 4s, what comes next? 3d. Is that right? So what will be the electron configuration for, say, scandium in the D block? It will be 4s2, 3d1. Is that right? If I take yttrium, what will be the configuration? 5s2, 4d1. If I take the elements below, it will invariably 6s2. Yeah, the 4f14 gets filled, but it will still come and end with 5d1. So how will you write the general electron configuration for the D block elements? NS2. Can you write ND? NS2 ND. Can you write it like that? Is it like this is 4 and this is 3? Is the N the same? So how will you write it? What letter will you write? N? Can I say it's N minus 1 D1? Right? For group 3, can I say this? Can I say that's the general electron configuration? Yes or no? Do you understand it? Does it make sense? Did I finish this notes page? Ooh, quantum numbers. I will do quantum numbers next class tomorrow. So please study for the quiz. You will have ions, you will have exceptions, you will have noble gas configurations, you will have loose dark structures, all this on your quiz. Is that clear? Okay? I'm done teaching now, so I'm going to stop.